because the last time I went this too quick. And this one basically is we have a way to graphically linking what we know analytically to show the locations of the characteristic root on the complex plane to the dynamic response of a system. Okay, so from here, usually we consider a dynamic systems like this. Okay, so for this case, from here you can see it depends on the zeta that can be possible underdamped, overdamped, quickly damped, or even undamped system. So using this example here depends on the value of the zeta, and we have the various possible situations. But anyhow, using this one, let me start with, say, for this case. And this one is called the underdamped systems. For underdamped systems, then we have the roots. The roots, the characteristic root is minus zeta omega n plus j okay. So that is the real part, and this is the imaginary part. We can place the root onto the complex plane. So this is the real part, and this is the imaginary part. Okay. And one of the features is such that this is the real part square, and this is the imaginary part. If you take such a calculation, then you take the sum of the square of those one, you can find that one actually equal to omega n squared. It doesn't matter what is the value of the damping ratio, this is always be true. Okay, so in this way, using the origin as the centers and using omega n as a radius, we can draw a circle. Then the locus, the root will be on this circle as long as omega n is determined. So once we know the system, the k over the spring constant or mass, then basically omega n is determined. Then that determines I would say locus for the distribution of the roots. Okay. So for example, if we have a certain damping ratio, and then that will make the minus zeta omega n to here, and that will make the omega n times 1 minus zeta to here. Okay, so that is the location of this root. Okay, and again, there, this equation basically is can be graphically represented by this radius, right? This radius has omega n. Okay, good. Again, in a similar way, here is a complex conjugate part, so always have the two parts. Okay, complex conjugate. Good. Okay. For this case, we can show the displacement. So again, this is a graphical representations, and let me use a different color to draw in the time response. So this is the graphical representations of the characteristic roots. We call the complex plane. On the other side, using this template, let me draw this one. So using the different colors in the complex, in the time domain, and right now I'm imposing the information is based upon what we have learned. And we know that based upon this one, we know the real part basically constitute the profile for exponentially decaying. That one I kind of repeated so many times. Okay, so that one is, this profile is exponent minus theta omega at. And again, this part is our real part from here. And oscillations, the frequencies of oscillation basically is determined by the, this is 2 pi divided by omega d, right? And actually this is our omega d. So oscillations frequency is determined by this magnitude, the magnitude of the amplitude, right? Okay. Any questions so far? Good. Okay, good. So we can pick up another point we can compare. So say we have a different damping ratio, and such that we have the different scenarios that corresponding. The root is here, and again, the complex conjugate is here. Okay. So now I'm going to draw the time response of this point compared to this one. So the time response, let me draw it here. Okay. Okay, now we have the graphically, we have a little bit more quantitative comparison. From here, you can see this is a real part. This real part is, in terms of magnitude, is less negative, right? This real part compared to this one, for example, this is minus 0.1. This could be, say, minus 0.7. Will that be right? Agree? Good. Okay. So if this is the minus 0.7, that's decaying quicker because this has the less negative, so it's going to decay slower. So you see right now I'm drawing the exponentially decaying. Right now I really reflect the more quantitative comparison. Compared to this one, this decaying faster. Be good? Okay. On the other side, this one, compared to its imaginary part here, that imaginary part is that big. So that means it has a larger omega d compared to this one, right? So in terms of oscillation, this system has the larger value of the omega d. What I mean? Compared to this one, it's going to oscillate quicker. Be good? So oscillate quicker, let me drawing is something like this. So it has more oscillations but decaying slower. Good? Okay. So this is a very important concept. And actually, what we have learned so far can be uniquely represented simply by this kind of graph. Okay, so that is for underdamped vibration systems. And we can further to explore other possibilities. So probably Doug, we can have a one new section.